In this video, we will talk about what the Fundamental Theorem of Calculus Part 1 says and give a rough proof of it. So I want to start with some background. In the previous section, in section 6.3 on definite integrals, we defined what a definite integral was, and a definite integral represented the signed area under a curve. So remember, signed area meant if our curve went above the x-axis, that contributes a positive area. If it went below the x-axis, that contributes a negative area. So now, in this section, 6.4, we are going to do the following. Let's look at the rate of change of the area function. So we're going to define a function for the area under a curve and look at its rate of change. And remember that rate of change, when I talk about the rate of change of something, this is talking about the instantaneous rate of change. So there's two types of rate of change. There's instantaneous rate of change and there's average rate of change. If a question doesn't specify which one it's talking about, average or instantaneous, it means it's talking about instantaneous rate of change. That is implied. Okay, and the instantaneous rate of change is the derivative. So we are going to look at the derivative of an area function. Okay, so let's set up our area function. We'll draw a picture and then we'll go about taking its derivative. All right, so I'm going to let f of t be a function that is continuous on some closed interval from a to b. And I'm just going to suppose that my function is always greater than or equal to 0. So it never goes negative on my interval. So this is just for simplicity. So the result we'll end up getting will apply even if my function ends up being negative, but just for simplicity's sake and to make an easier picture, I'm going to assume that f of t is always greater than or equal to 0. And now I'm going to define an area function. So I'm going to call this g of x. It's an area function, so I need a definite integral. And my definite integral will be the integral of f of t, but I'm going to start it at a, whatever value a is, and end it at x. So it's going to start at a constant a, and the upper limit is x, a variable. Okay, so drawing a picture to represent what it is that we're talking about. If I draw some axes, so this would be a t-axis, this would be my y-axis, because f is a function of t here. So if I were to draw some graph of a curve, I'm going to call this y equals f of t. Let's say that it has this sort of shape. And let's say that a is here and b is somewhere further down the road. What g of x represents is it's the area under the curve f of t on the interval starting at a up until whatever x is. So let's just say x is somewhere there. So g of x would be this area, the area under the graph, in between, over the interval from a to x. So our goal is going to be to compute the derivative of this area function, g prime of x. Okay, so now I have to do a little bit of review from Math 30, from the previous calculus course, how we compute derivatives. So let's recall from calculus, the previous calculus course, or at Santa Clara, that would be Math 30, that the derivative, g prime of x, the formula for that involved the limits. That was the original definition of a derivative. So one of the ways to write that was the limit as h approaches 0 of g of x plus h minus g of x all over h. Okay. And one thing I wanted to just mention here, I said it out loud in words, but let me just write it down, is this area right here is what g of x is. So g of x is this area under the curve between a and x. All right, so now we're starting to set up this derivative, and we're using the limit definition of the derivative. Okay, so I'm going to draw the picture one more time. So I'm going to draw my y-axis and my t-axis, and I'm going to draw this curve one more time. So this curve one more time, and let's draw where a is and b is, but this time I'm going to draw x and x plus h. Okay, so I'm going to draw a line up from where a is, and I'm going to need to compute this limit. So let's start with the numerator of this limit and break down what it means. So the numerator is g of x plus h minus g of x. Well, what is g of x plus h? So thinking back to what g of x is the area under the curve y equals f of t. Oh, I'm sorry, I should label that here. This is y equals f of t as well. Is the area under that curve over the interval from a to x. So in that way, g of x plus h would be the area under the curve from a all the way until x plus h. G of x is the area under the curve from a to x. So the first term is the whole area all the way up until x plus h. The second term is the area from a all the way until x. When we subtract them, what we would be left with is the area from x to x plus h. Okay, and the reason for that is the first term is the area on the interval from a to x plus h. The second term is the area on the interval from a to x, and we're subtracting those two areas. And when we subtract them, we end up with the area on the interval from x to x plus h. Okay, so we need a way. What I'm going to try to do now is I'm going to try to estimate the area under the curve from x to x plus h. And we've talked about how we can estimate the area under a curve. We can do it using a rectangle. So I'm going to draw a rectangle using left endpoints. So for this subinterval from x to x plus h, I'll use left endpoint, go up until I hit the curve, draw a horizontal line for the top, and then draw a line down, and there I have my rectangle. All right, so the area, the exact area under the curve from x to x plus h is approximately equal to, so this is, let me write that better, this is approximately equal to the area of the rectangle that we just drew above. So again, it's important that you know that this is a squiggly equal sign. This means approximately equal to. And what's the area of the rectangle? Well, I have to do base times height. And the base of the rectangle, so distance from x to x plus h would be h. That's the base. And the height, well, which of these x values did we plug in to get the height? Well, I use left endpoint, so I plugged in x into my function to get the height. So we get f of x for the height. So h is the base. This is the base, and f of x, that is the height. So what we have now here is, remember, we were evaluating the numerator. Let me zoom it out a little bit so I can look at this whole thing. We were trying to compute this limit definition of the derivative over here, and we have approximated the numerator. The numerator, g of x plus h minus g of x, we started to work out, and we've gotten that that is approximately equal to h times f of x. So now, let's divide that by the h that's on the denominator, and then we'll take the limit. All right, so let's take our difference, g of x plus h minus g of x, though that was our numerator, and let's divide it by that h that we need on the denominator. Well, this is approximately equal to, I know what the numerator is approximately equal to. It was approximately equal to h times f of x. That's what we just got. It's approximately equal to h times f of x. And then we have that h on the bottom now. We're dividing by this h. And then the h's cancel, and we get f of x. Okay, so this whole fraction, g of x plus h minus g of x, all over h, is approximately equal to f of x. And it's approximately equal because the area of that rectangle was approximately equal to the area under the curve. So if we look back to this picture here, this approximation gets better and better and better the smaller we let h become. As h gets closer and closer and closer to 0, this rectangle and this slice sort of area under the curve gets smaller and smaller and smaller, and my approximation gets better and better. So going back to where we were writing our work, we have this approximately equal sign here. But as h approaches 0, as we take the limit as h approaches 0, our approximation becomes exact when we take that limit. Okay, so that's what we can do next. Let's take that limit. Let's take this limit as h approaches 0. So the limit as h approaches 0 of g of x plus h minus g of x all over h. Once we take that limit, this is the derivative. This is the derivative of g. So that's g prime of x. And then that approximately equal to will become exactly equal to what we have on this other side, which was f of x. So we've just shown that the derivative of g equals f of x. That's what we wanted to show. Or actually, I'm getting ahead of myself a little bit. We've actually just proved a key result that I'm about to write below. So we have just sketched. There's some details here that we would need to make a little bit more rigorous to make this a very formal proof, but this is the overarching idea. So we have just sketched the proof of the following result. The following result. This is called the Fundamental Theorem of Calculus, Part 1, which I'll abbreviate as FTC 1. And what it says is, if f is a continuous function on the closed interval from a to b, and g of x is this area function, the definite integral from a to x of my function f of t dt, so it's the area under the graph of f from a to x. So that's how g of x is defined for any value of x that's in between a and b. Then what we just showed above is that the derivative of this area function, g prime of x, is equal to that function f, but with an x plugged in instead of t. That's what we ended up getting. We got g prime of x equaled f of x. So an equivalent way of writing this would be the following. So what we've just shown is that the derivative of g of x equals f of x. Another way to say that using the word antiderivative is equivalently g of x is an antiderivative of f, the function that we started with. So it's an antiderivative of f of x. So what was g of x, though? G of x represented an area. So what we're saying here is, if I have a function f of x, the antiderivative of it is connected to an area under its graph. And that's a remarkable result. We're going to make this a little bit more formal, and that's going to become the Fundamental Theorem of Calculus Part 2, which we'll eventually show. And that'll drastically reduce the problem of finding the area under a graph to simply just computing an antiderivative and plugging some stuff into it. So in terms of our goals for this section, we have finished our first goal, which was to give a rough proof of part 1 of the Fundamental Theorem of Calculus. In the next video, we will do an example using this result.